Hello everyone, my name is Rodolfo Castillo. I'm a PhD candidate at University Laval under the supervision of Professor Benoit Fournier and Joseph Dunchen. Today, I'm going to speak about my research work, that is the development of a new accelerate methodology to assess the potential oxidation reaction of sulfide-bearing aggregates on concrete specimens. Here you have the agenda that I'm going to share with you today. So we are going to start with the context of the project. This project emerged because there was a big issue on the city of Trois-Rivières. It's a small city between the city of Quebec and Montreal, Canada, where two quarries were supplying concrete aggregates with a highly quantity of iron sulfate minerals. These iron sulfate minerals you can see here in the picture are in a brownish or yellowish color, and they are composite of iron and sulfur, so they can be really attacked by the environmental condition. As you can see in the picture above, there is a lot of erosion already done on the rock material. So when we use this type of aggregates on concrete, two main reactions will happen if water and oxygen are available on the system. First is the oxidation process, and the second is the internal sulfate attack. I will explain in detail in the next slides. So for the oxidation process of the iron sulfate minerals we have the iron sulfate minerals, principally pyrrhotite is the most reactive one, that can be activated by the oxygen and the water, so the iron will be released and will continue uh, reacting with the oxygen and water available on the system to form the iron oxides or the iron hydroxides, as you can see here below. And we know this is the most common is the rust material, but this is not the only one reaction. So after the oxidation process is done, the iron sulfate mineral will continue releasing sulfur, and this sulfur will transform in sulfuric acid that will attack portlandite to transform in gypsum. And if we have water and alumina source from the cement paste, the C3A, it will transform in ettringite. And if we have the ideal conditions, like a source of carbonates, the silicium from the cement paste, and more water, we can form thaumasite. And thaumasite is a really destructive mineral for the cement paste. You can see here in the picture a concrete affected by this reaction. Normally, there will be a whitish color around the aggregate. We say O-ring, and this O-ring is an indice that there is a several internal sulfate attacks already happened on the cement paste. Both reactions mentioned before will create secondary products that are really expensive. So they will start creating micro cracking on the cement paste until it reaches to the surface, as we can see here, in a really map cracking, a bigger size and map cracking effect. So for this problem, there was not a easy solution, and the only solution that they could think it was to lift the houses, and the people were living there for around 2 months, and after that they reconstruct the foundation and then deplace the house again on the site. So now I'm going to talk about the literature review that I have been done for this project. During 2010 to 2015, there was a big project at University Laval to try to develop a protocol to evaluate the potential oxidation reaction of the sulfide-bearing aggregates that consists in a step-by-step issue. So the first step is to prepare the samples, and when after the sample are prepared, there is a total sulfur test that is to quantify the sulfur on the aggregate, and then is an oxygen consumption test that is to see how the oxygen is consumed by this type of aggregates. And finally, a mortar bar expansion test where we measure the expansion to see how these products will be creating in different conditions. So there are two different conditions on this mortar bar test. Is the oxidation with high temperature and low relative humidity, and the other condition that is low temperature and high relative humidity. But there is not only one oxidation reaction in civil engineering work, so there is another type of oxidation reaction in concrete elements that we know as corrosion. As you can see here on the pictures, there is the iron attached to the steel bar that can suffer by the oxygen and water available and other agents that can accelerate or promote this type of reaction. So a particular case grabbed my attention because there is something that we call pitting corrosion. And this pitting corrosion happened when chlorides arrive to the system. And this chloride will attach to the iron that is being oxidizing. So this will create new products, and these products will release to the pore solution. Unfortunately, these new products are not in good connection. They don't have good connection, so they will separate, and the iron will be free on the pore solution, making available to the oxygen and water more easily to create more rust products. This is a way that we can accelerate or improve the corrosion in the steel bar. Based on all this information, I developed my research program. Now you can see the big picture of my research project that start with the making new concrete under laboratory conditions, and we select two types of improvement of the oxidation with two different techniques. Today, I'm going to concentrate just in one, that is the electron migration treatment, that consists in the chloride impregnation and the impressed voltage test. I will explain in detail later to generate or improve the oxidation. And then we try to pass these specimens to a condition to generate the internal sulfate attack with low temperature and high relative humidity to see the performance of the aggregates after being submitted to this treatment. Now I'm going to talk about this methodology, how I developed this methodology. So this methodology starts with the chloride impregnation of the electrochemical treatment. It's when we put a concrete specimen in an electromigration cell, and with a helping of the voltage we generate the electrolysis of water, and chloride will be free on the system. This chloride will try to migrate to the positive part of the electromigration cell within the time. So we just need to wait. This chloride little by little will be migrate in all the length of the concrete specimen until reach to the other part of the solution. But it's really important to say that we need to control different parameters to avoid different attacks and cannot be involved on the damage of the sulfide-bearing aggregates. The next step is to maintain this current for a long period of time to, to improve this oxidation reaction of the sulfide-bearing aggregates. And this part we call the impressed voltage test. To reformulate this testing for our purpose, I have to try with different materials, and during the early 2020s, I started working to develop a new electrode that can allow me to have the condition that I explained before. So I tried with different materials, and we found that the graphite was the better material for the purpose of my project. So the next step was to develop the electromigration setup because we have some setups already for the RCPT, but we need the long length of the concrete specimen so we can try different testing later to evaluate the damage or the detrimental effect of the sulfide-bearing aggregates. And here you have a picture of the final setup that I developed for these purposes. Once the setup was properly developed, I had to confirm that the chloride impregnation was done on my specimens. So I started with a non-reactive aggregate to try to migrate chloride into the other part of the length of the specimen. So we tried the electrochemical treatment in a different timing to see at what time we can reach our total impregnation of the chloride. As you can see here in the picture, at 3 days, 7 days, 10 days, and 14 days, how the chloride was migrating in my concrete specimens. And I use a colorimetric measurement by applying silver nitrate, spraying silver nitrate in the concrete specimen. And we can see here in a gray or whitish color is the chloride profile advancing inside to the concrete. Finally, after having the setup complete and controlling all the parameters and trying with a non-reactive aggregate to see our chloride impregnation, we go to the next step that is to testing our reactive material. And as you can see here in the picture, it's concrete specimens using the sulfate-bearing aggregate material from the quarry of Tuparribia. So this aggregate, we select some from stockpiles, some aggregate with a highly quantity of material. So this is a over charge of sulfate aggregate because we want to confirm first if this treatment can generate some reaction. And as you can see here in the picture, we can already saw after 14 days of treatment, we already saw some spots of with pop-outs, with rust products. And if we apply 7 more days of in press voltage test, we can see how it's highly deteriorate the concrete specimen due to this detrimental reaction. So now we can have a proof of that, and this electrochemical treatment is already published, so you can download it and you can search the paper where I speak how I developed this electrochemical treatment to activate the oxidation reaction of the sulfide-bearing aggregates. Now I'm going to present some results about this development of this methodology. When we talk about results, it's always in the beginning that appears the question how to measure. The most important thing is that we already generate some damage in the concrete by the electrochemical treatment, activating the oxidation reaction of the sulfide-bearing aggregates, but we need to know how to measure this damage and if it's really contributing to decrease some properties of the concrete, and we need to evaluate how it's going to be affected. So we go through it and we do some compressive strength, some stiffness damage test that is a cycling testing, small cycling testing on concrete specimens consisting on 5 cycles of compressive and decompress of the specimen, and we can measure the modulus of elasticity and some other index. The damage rating index, like in a concrete polished section, we try to quantify in squares the 1 milliliter, 1 centimeter by 1 centimeter, the number of cracks in the cement paste or in the cracks with different products, the ultrasonic pulse velocity, electrical resistivity, and the expansion test to see which measurement can allow us to distinguish between a reactive and a non-reactive aggregate. So we do all this testing for a series of two aggregates that I'm going to present in the next slide. As I mentioned in the slide before, we do this testing for two aggregate material, one reactive and one non-reactive. The reactive one we identify as MSK 0.9 and the non-reactive material is PKA. These aggregates are similar, not the same, but they are similar to see how it's gonna be the performance of each after the electrochemical treatment after 14 days, 20 days, 35 days, and 56 days, and see if we can find, as I said before, a measurement that can allow us to distinguish when we have a reactive and when we have a non-reactive material, or if we can say to evaluate the potential oxidation reaction of this type of concrete materials. After performing all the testing mentioned before, we found that the modulus of elasticity was the measurement that can show us how the evolution of the detrimental reaction of the sulfide-bearing aggregate. You can see here in the graph at 28 days of curing the performance of the concrete and how it decreased within we apply more electrochemical treatment with the time 14 days, 28 days, 35 days, and 56 days. And you can see here in the picture that at 28 days of curing, the iron sulfate minerals were not touching, were not affected. But while the chloride reached to the surface of these iron sulfate minerals, we can see here how can be affected by this reaction. Normally the reaction will start in the periphery where the chlorides will reach to touch the iron sulfate minerals and will oxidize, and then these byproducts will generate expansive reaction forming cracking internally and to the cement base too. But the most important result is from the aggregate of pKa, we are not generate any loss of the modulus of elasticity, so that can allow us to distinguish between a reactive and non-reactive material. The problem is that because they are different aggregate, they are from a different quarry, the performance is not the same. So for that, we need to create a new measurement that can allow us to compare between one and another type of source of aggregate. To be able to compare two different sources of aggregate or another source of aggregate, we are proposing a new measurement that we call relative modulus of elasticity, and is based on the modulus of elasticity obtained at 28 days of curing compared with the results that we obtain after some electrochemical treatment, 14 days, 28 days, 35 days, or 56 days. And I presenting here how the concrete performance after this treatment, and you can see here the reactive aggregate, how it's losing on this property, while in the pKa it's gaining some on this property due to the hydration of the cement paste. So what I can say is like here we observe something really important, that is that after 35 days of electromigration treatment, we don't really see an increase on the um, losing of the performance of the concrete. So we think that with this percentage, we can really distinguish between a reactive aggregate and non-reactive aggregate. So here you have an example of a concrete polymerization after the electrochemical treatment, 35 days of electrochemical treatment. And it's difficult to see in the screen, but if we do a zoom, we can really observe the concrete affected by this reaction. And here Here you have an example of the pKa material, the aggregate material, that is not affected by this reaction if we can make a zoom, we cannot observe any cracks, rust products, or cracking on the cement paste due to this oxidation reaction. Sooner than later, the paper talking about all these experiments will be published soon, where I present all the results, the non-destructive testing, the destructive testing, and all the condition and ideal parameters to measure the detrimental effect of this oxidation reaction, and how this measurement can allow us to distinguish between a reactive and non-reactive aggregate material. After being defined the way we can activate and accelerate the oxidation reaction of the sulfide-bearing aggregates, and how can we measure if there is some damage on this concrete specimen with ideal timing and parameters, now we are doing some other testing with different aggregate materials with different sources, principally with another worldwide known aggregate knowing that present some reaction on site. It's from Connecticut, USA, and another aggregate from the Trois-Rivières region that it's not really reactive, but probably is on the limit that can present damage in concrete materials. And now I will present you how the concrete specimen finished after the 35 days of the electrochemical treatment with the Connecticut aggregate. And you can see here how it's really affected with the rust products and a lot of crack going and some pop outs also, and really big cracks with orange and yellowish color due to the sulfide-bearing aggregate reaction. At the same time, I would like to share with you this concrete poly session of the Connecticut aggregate with a sulfide-bearing aggregate, and you can see here it's difficult, but there is crack already happening on the after 35 days of electromigration treatment. And if we make a zoom, we can see clearly how these open cracks in the aggregate transfer to the cement paste with rust products surrounding the crack. Now I will present some conclusion and perspectives. In conclusion, this new methodology can evaluate the potential oxidation reactivity of the sulfide-bearing aggregates under laboratory conditions in a shorter period of time, and the poly section showed that the wetting of the crust are highly correlate with the bigger loss of the modulus of elasticity. Also, measurements of the modulus of elasticity are the more parameters to evaluate the potential Harmon reaction of the sulfate-bearing aggregates, and the proposed relative modulus of elasticity can really show the distinguish between a reactive and a non-reactive aggregate. In our perspectives, we are working now in a new code on the damage rating index related to the oxidation reaction of the sulfate-bearing aggregates. Sooner than later, we want to complete our testing protocol with a completely methodology for evaluate the potential oxidation reaction of sulfide-bearing aggregates. At the same time, we are working with alkali-silica reaction aggregates under electrochemical treatment, and more aggregates from different sources and with different total sulfur are being performed with this methodology. So thank you so much for your attention, and thank you to the Rilem Youth Council to invite me today to present my research work. And I also would like to thank our research partner to allow us to do this investigation. I'm here to listen your question.